Hello everyone, I am Ponnakirti BL. Welcome to LangChain tutorial from Python to GenAI. In this series, we will learn how to move from Python fundamentals to building real-world generative AI applications using LangChain. We'll explore key concepts like agents, chains, memory, and model integration. Everything you need to start building intelligent AI systems step by step. So let's dive in and start today's session. Today's topic is LangChain Essentials, the key components for building GenAI apps. Build powerful RAG-based GenAI apps. Let's start with introduction. Imagine you are building an AI application that can answer questions from hundreds or even thousands of PDF documents. Would not it be great if the system could search across all these files and respond intelligently, almost like chatting with your data? That's exactly what LangChain helps us to do. So, in this lesson, we will explore the core components of LangChain that make this possible. These are the building blocks behind GenAI application like Retrieval-Augmented Generation. In short, we call it as RAG. Before diving into coding, it's crucial to understand how these components work together, from loading data to splitting text, creating embeddings, storing them in a vector database, and finally retrieving relevant information using a language model. So this is introduction. Let's understand what is retrieval augmented generation called, also we call it as RAG. Let's start with concept of RAG, retrieval augmented generation. Think of RAG as a smart bridge between your private data like PDFs, Excel sheets, or web pages and powerful language models such as GPT or Gemini. So here's the simple idea. You have a data source, maybe thousands of PDF documents. You build a GenAI applications that allows user to ask questions in natural language. So when a user asks a question, your app does not rely on the model's training data alone. Instead, it retrieves the most relevant information from your PDFs, augments the prompt with the context, and then generates an answer. This combination of retrieval plus generation is what makes RAG so powerful. For example, if your PDFs contain software release notes and something asks what's new in version 4.2, your app fetches the relevant section from the right PDF, provides it to the LLM, and produces a clean and summarized answer. Here in diagram, you are able to see user queries. It will go to retrieval, then it will generate LLM answer. So the retrieval part will be PDFs, databases, text files, any data source. This is what the RAG is. Next, we can go for key components in LangChain. To build such a system, LangChain provides several modular components. Let's go through them step by step. So these are the modular components: data source, data splitter, embeddings, vector store, retriever, and LLM. So let's start with data ingestion, getting the data in. The first step is data ingestion, loading your data into the system. LangChain supports many data formats like PDFs, Excel and CSV files, JSON files, images, websites, and URLs, even videos and text files. Depending on your project, you can use different LangChain loaders to read and process these files. Why it matters? Before your model can answer questions, it must know your data. So ingestion is like feeding knowledge to your application. So you are able to see data ingestion funnel, which can be an LangChain engine for ingesting the data. Step 2 will be data splitting, breaking data into chunks. Once data is loaded, next step is split into smaller chunks of text. Why do we need to split the data? Language models have context limit, meaning they can only handle a certain number of tokens or words at a time. For example, GPT 3.5 may handle up to 16,000 tokens. Llama 3 or Gemini Pro may handle more but still have limits. So instead of giving the entire PDF, which could be hundreds of pages, we divide it into manageable pieces, maybe paragraphs or sections. These smaller pieces are called text chunks or document chunks. For example, if we have a 50-page PDF, LangChain might split into 200 smaller chunks of 500 words each. This ensures each chunk can fit comfortably within the model's context window later. This process falls under data transformation since we are reshaping the data to make it model friendly. So this completes second step. Let's go with third step, text embedding, converting text into vectors. Now comes one of the most critical steps, embedding. So when humans read, we understand meaning. Computers, however, need numbers. So we convert each text chunk into vector, a list of numbers that represent the meaning of the text in mathematical space. This process is called text embedding. So here you are able to see hello world is the text that will be converted into embeddings like numeric values. So why do we need embeddings? When a user asks a question, we want to find the most similar pieces of text from our data. To do this, we use similarity search, often based on cosine similarity, to compare the question's vector with all stored vectors. For example, your query will be what's new in version 4.2. The system finds the text vector most similar to query vector. Maybe in version 4.2, we added a new API endpoint for the data export. So, which are the embedding models we have? OpenAI embeddings like text embedding 3 small. Then we have Hugging Face models, open source, and Google Gemini embeddings. Each has its own strengths depending on the use case. Next, go with step 4, vector store, saving and retrieving vectors. After embedding, we must store the vectors efficiently. This is where vector database come in. A vector store DB is a special database designed to handle vector data and perform fast similarity searches. Common vector stores include FAISS by Meta, ChromaDB, AstraDB, Pinecone, Viviate. These databases let you store the text embeddings, perform similarity searches to find relevant context quickly. So when a user asks a question, the system queries the vector store and retrieves the most relevant chunks of a text as a context. So the third step is the retrieval and generation process. So user asks the questions, retriever searches vector DB, then context retrieved from PDF snipped, then prompt template added, then we will get the LLM response generated. Now that our data is embedded and stored, let's see what happens when a user asks a question. The user's query is received. The system creates a prompt which tells the AI how to behave. For example, you are an AI research assistant, answer questions based on provided context. The query is sent to the retriever which searches the vector database for similar chunks. This part is managed by LangChain's retrieval chain. The retrieved chunks called context are combined with prompt. The combined text is sent to the language model. The LLM generates the final answer based on both the question and the context. So, retrieval brings the right information and generation crafts the final human-like response. So, important LangChain components to remember. Data loader reads data from files or sources. Text splitter divides large text into smaller context size chunks. Embedding model convert text chunks into vector forms. Vector store DB saves embeddings and perform similarity searches. Retriever finds relevant context from the vector store. Then we have prompt template defines the LLM role and response style. LLM model generates the final natural language answer. All these components together form the RAG pipeline. So what's coming next? In the next lessons, we will implement each of these steps hands-on. How to perform data ingestion with different data sources. How to split and pre-process large documents. How to create embeddings using OpenAI or open source models. How to store and search them in vector database like FAISS or Chroma. And finally, how to build full retrieval chain that connects your data to the LLM. Each of these steps will be demonstrated through mini projects that led up to complete RAG-based GenAI app. So let's recap what you learned. By the end of this session, you now understand what RAG, that means Retrieval-Augmented Generation means. Next, why LangChain is essential for building data-aware GenAI applications. The 5 key steps in RAG pipeline are data ingestion, data splitting, text embedding, vector store, retrieval and response generation. These are core pillars of every real-world GenAI project you will build with LangChain. In the next video, we will begin the data ingestion techniques, exploring how LangChain connects to different data sources, how to prepare them for our AI pipeline. So thanks for watching today's session. This is part of LangChain Bootcamp from Python to GenAI. If you found it helpful, please subscribe to my channel for more lessons on building with LangChain and Generative AI. Also feel free to connect with me on LinkedIn. You will find the link in the description. See you in the next session. Thank you very much.